Myself, JV and Dr. Kiran Yadav. In this session, I will discuss about the Compton effect. The Compton effect was first demonstrated in 1923 by Arthur Holly Compton, for which he received a Nobel Prize in 1927 in physics. The Compton effect is also called Compton scattering, is the result of a high energy photon colliding with a target, which releases loosely bound electrons from the outer shell of the atom or molecule. The scattered radiation experiences a wavelength shift that cannot be explained in terms of classical wave theory, thus lending support to Einstein's photon theory. Probably the most important implication of the effect is that its short light could not be fully explained according to wave phenomena. Compton scattering is of prime importance to radiobiology, and it happens to be the most probable interaction of high-energy X-rays with the atomic nuclei in living beings and is applied in radiation therapy. In material physics, Compton scattering can be used to probe the wave function of the electrons in matter in momentum representation. Compton scattering is an important effect in gamma spectroscopy, which gives rise to the Compton age, as it is possible for the gamma rays to scatter out of the detectors used. Compton suppression is used to detect stray scattered gamma rays to counteract this effect. In this experiment, a graphite target was bombarded with monochromatic X-rays and the wavelength of scattered radiation was measured with a rotating crystal spectrometer. The intensity was determined by a movable ionization chamber that generated a current proportional to the X-ray intensity. Compton measured the dependence of scattered X-ray intensity on wavelength at three different scattering angles of 45 degree, 90 degree and 135 degree. The experimental intensity versus wavelength plots observed by Compton for the three scattering angles show two peaks, one at wavelength lambda of incident X-rays and the other at a longer wavelength lambda dash. So this is how the Compton effect works. So an X-ray photon is incident on an electron, then the electron gets scattered and the X-ray photon also gets scattered in other direction. The incident photon has the following energy E and linear momentum P. E is equals to hc upon lambda and P is equals to E upon z. Analyzing these energy and momentum relationship for the photon and electron, end up with three equations, which gives energy, x component of the momentum, y component of the momentum in four variables. These four variables can be phi, the scattering angle of the electron, theta, the scattering angle of the photon, E, the final energy of the electron, E dash, the final energy of the photon. If we care only about the energy and direction of the photon, then the electron variable can be treated as constants, meaning that it's possible to solve the system of equations by combining these equations and using some algebraic tricks to eliminate variables. Compton arrived at the following equations: 1 upon E dash minus 1 upon E is equals to 1 divided by MEC square multiplied by 1 minus cos theta. Or in terms of wavelength, we can write the equation as lambda dash minus lambda is equals to h upon MEC into 1 minus cos theta. The value h upon MEC is called the Compton wavelength of the electron and has a value of 0.002426 nanometer. So this is the Compton effect. This is